Today we are going to study about Brillouin zones. So first of all, what are Brillouin zones? So if an electron is moving in a constant potential, then it will move freely in a particular structure. While if the electron is in a periodic potential, it means that the ions are arranged periodically in a lattice, and the electron is feeling the periodic potential of the positive ions. So when we talk about this potential, what we mean is that because this is a line of positive ions, and the potential associated with positive ions will be actually dependent upon 1 upon r, and therefore it will decrease as we move away from the ion. So that is why this potential looks like this. So because of this periodic potential, what will happen is that, or the periodic arrangement of the ions, which has periodic potential automatically. So because of this periodic arrangement of the ions, the electron will get diffracted by this periodic arrangement of ions. So this diffraction of electrons is similar to the diffraction of electrons which we have studied for light or for X-rays, or even for electrons when we are studying diffraction of electrons in transmission electron microscopy. So if we have two planes which are separated by a distance d, then you know that Bragg's condition can be found out. And if suppose the incident wavelength is lambda, which might be an electron or a X-ray photon, so the Bragg's condition will be 2d sine theta is equal to n lambda, where d is the interplanar spacing. So in the similar manner, if this electron is incident on these planes, so here just for clarity's sake I had drawn only one line of these ions, but in actual there will be many lattice planes. So suppose that we have two lattice planes at a distance a from each other. Then if an electron with a wave vector k vector, so k is nothing but 2 pi upon lambda, which is the wavelength of the electron wave that we are talking about. So this diffraction that we are discussing will be discussed because of the wave nature of the electron, and when we are discussing the wave nature, then k vector comes into picture. So then these electrons, they get diffracted from these planes, and because of this diffraction, the diffraction will occur only at certain conditions, and that will lead to Brillouin zones, which we will discuss gradually. So suppose that if this is a two-dimensional lattice, where and this is actually a real space where the interplanar spacing or the interatomic spacing is a, then if we compare these two situations, then we can write 2a sine theta is equal to n lambda, and we can replace lambda by 2 pi upon kx. Let us say that this direction is kx and this direction is ky, so the interplanar spacing will be kx in this case. From here we can find out kx is equal to n pi upon a sine theta. So now this will be the Bragg condition for diffraction in a square lattice. We see that diffraction will occur only when this condition is satisfied. So if lambda is of the order of a, which is the interplanar spacing, or n times of a, less than a or equivalent to a, then diffraction will take place. So but if the wavelength is very large as compared to a, then the electron will move freely and there will be no diffraction taking place. So if in the K space, now how do we draw this diffraction with these Brillouin zones? So suppose that we are taking this atomic arrangement we are converting it from real space to a K space. So in K space, where the distance between two ions will be pi upon a. So rather 2 pi upon a. If you take one of these ions and you draw, take the nearest neighbors and you join those nearest neighbors and take half of them. So in K space it will be a Brillouin zone. In real space, if you do that, then this distance will be a, then it forms a Wigner seed cell. So it means that Wigner seed cells in real space is actually, if you convert it into K space, turns out to be a Brillouin zone. But in simple language, in K space, you just take nearest neighbors, join them, take half of them, and the space that is created by that will give you the first Brillouin zone. And this first Brillouin zone will actually extend from minus pi upon 2 plus pi upon a, because you see that this distance is pi upon a. So half is 2 pi upon a. So half of it will be pi upon a and half of it will be again pi upon a. So the total distance of the first Brillouin zone will be minus pi upon a to plus pi upon a, which will be 2 pi upon a. So this is how we form the first Brillouin zone. So in this first Brillouin zone, we can draw the energy contours will be like this, because you know that energy is given by h bar square k square upon 2m. So in kx ky space, and a circle, this will be the equation of a circle, and a circle will give you equal energy surface. So on that circle, the energy will be constant. So if the k value is smaller means lambda is large, then it will not get diffracted and it will be a circle. And if the wavelength is of the order of pi upon a, or k is of the order of pi upon a, or lambda is of the order of a, so what we are saying here, that either k is of the order of pi upon a or lambda is of the order of a, then there will be diffraction taking place at these edges, and because of that the deterioration of this circular energy contour will take place. Because of this, the energy contours, they are deteriorated as you move nearer to the Brillouin zones due to diffraction at the edges. So Brillouin zones is nothing but and the diffraction of electrons taking place. So you know that we have a range of energy and we have a range of interplanar spacings which will be a, 2a, 3a, 4a, and therefore and electrons are also not single energy electron that is present in a crystal. There might be a range of electron energies that might be present in a crystal, and because of which a particular different set of electrons will be diffracted by a different set of interatomic planes, interplanar spacings. So this is also, we have also, you might have also found EK diagrams like this, where this case was for a situation where electron is in a constant potential or in a zero potential, then you get this parabolic EK diagram. But when you solve the Schrodinger's equation for an electron which is moving in a periodic potential, as we discussed in the last few pages, we see that if it is a periodic potential, then instead of this EK diagram to be parabolic, it actually breaks down in such a manner that in the red one is actually for EK diagram for electron in a periodic potential. So when an electron is a periodic potential, you would see that naturally you have this energy band gap. So these are allowed energy, and this is and the energy values that are not allowed. So the electron cannot possess these energy values. So electron can have this energy value, it can have this energy value, but it cannot have this energy value which is not allowed. So this also leads to energy band diagram which we know. So it will have these allowed energy ranges and these forbidden ranges of energy. So also if you see this EK diagram, just in the first Brillouin zone from plus pi upon 2 to minus pi upon, from plus pi upon a to minus pi upon a, you'll see that initially when k is small, it means lambda is very large as compared to a, then it follows parabolic potential. It follows the parabolic nature of the dispersion relation EK diagram. But as you move away from this range and you approach the Brillouin zone, or lambda becomes of the order of a, then it deviates from this parabolic nature. And this is because of the diffraction taking place at the edges. So similar is not also true for second Brillouin zone, which will be from pi upon a to 2 pi upon a, and the third Brillouin zone from 2 pi upon a to 3 pi upon a. It means that this energy range will stay, electrons will stay in this k value, while this energy range will stay in this particular k value. So if we draw a particular, if we draw just this part of the spectra and see what happens in different materials, where let us say that one of the bands is the conduction valence band and the other one is the valence band. So because electron diffraction will take place in all materials, irrespective of if it is a metal or a semiconductor. So it means that if Brillouin zones are present in all materials, it means that it will also be present in metals. So it means that forbidden gaps will also be present in metals. So if they are present in metals, then how are metals behaving as conductors? They should not be behaving as conductors, they should be behaving as insulators or semiconductors. But in actual they are behaving as conductors. This is because if we draw the EK diagram in X, Y and Z direction for a metal, you see that they do have these forbidden bands in the Brillouin zone, and they do have Brillouin zones and these forbidden bands, but what happens is that these overlap with other energy values. So you see that this energy band is taken care of by this allowed k values, then this energy band is taken care of by these allowed k values. So it will just behave like a tube of water, where you see that the water can flow from so the electrons can actually flow from one state to the other, and it will not face any forbidden band. And on the other hand, in a semiconductor, you see that in all the three directions there will be a forbidden band, and there will be no overlap of the bands, and therefore it will lead to the semiconductor or the insulating nature of a particular material. So we can also understand various insulating and conducting materials based on the type of occupation of the Brillouin zone levels that is taking place. So let us say that we have drawn the first Brillouin zone and the second Brillouin zone here. So I think I forgot to discuss about the second Brillouin zone in this diagram. So you see that if you take the nearest neighbors and you bisect the line joining the ion at the center to the nearest neighbor, which we were discussing here. So if you divide it into two, and then you will get the first Brillouin zone, and then you take the next nearest neighbor. So in this situation, this will be the next nearest neighbor, and you take a half of it. So if you take a half of it, this will be this will give you the second Brillouin zone, while the first Brillouin zone was you have to take the half of the nearest neighbor, first nearest neighbors, and then you take half of the second nearest neighbors, and so on. So you will get all the Brillouin zones. So this is how we found the second Brillouin zone. So we have drawn the first two Brillouin zones for diamond, sodium and magnesium, and you see that in diamond, because the valence band will be completely filled and conduction band will be completely empty, so it will look like this. So the first Brillouin zone will be completely filled and the second will be empty, creating a forbidden gap. Brillouin zones is nothing but a forbidden gap, because as the electron will move from center to near the edge of the zone, it will get diffracted, and so if it is coming from here to here, it will get diffracted and then it will move in this direction, and so it will not be able to go out. So that is equivalent to a forbidden gap in energy band structure. So also in sodium, you see that this is an energy, this is the configuration, electronic configuration, and the 3s band is half filled. So it means that only few energy levels will be occupied and rest of them will be half. will be vacant. So this red actually is depicting the full filled energy levels, while which are clear, they represent vacant energy levels. While in magnesium, you see that magnesium also has an electronic configuration which seems to be of that of a semi insulator, because the band is completely filled, and the next band that is available, it will not be able to jump because of the forbidden band gap. But you see that in magnesium, s and p orbitals, they overlap. Because of it, the half of the energy band of s will be filled and half of p will be filled, and that is why electron can move from one band to the other very easily, making magnesium a conductor.